So in the last class, we were having a discussion on the aspects of image sampling and quantization. Sampling was basically what we saw in the spatial domain, and there we said that we must sample, okay, at least at a spatial frequency which will be higher than twice the maximum bandwidth content. And then we also discussed about the aspects of image quantization in its intensity levels. And we had also discussed there that if we increase our sampling resolution, okay, then I mean the amount of bits which you require to store gets proportional to the I mean dimension of the image. So that means to say that for an n by n image we have got order of n square for the storage complexity. And then we had also discussed about the number of quantization levels which we keep in the intensity, and there we found that for a better resolution, okay, for a better quality of picture, we need more number of bits, obviously, means more number of quantization levels rather, but there is always a trade-off that gets involved. Means if we have more number of quantization levels in intensity, that improves our picture, no doubt, but one thing that our ultimate detector is eye, so whatever our eye can discriminate, only those many levels are going to be sufficient for us. And the second point is that if we increase the number of quantization level, that automatically increases our total storage space. So there is always a trade-off between the total storage space to store a digitized image and the quality of the image. Now today we will see some analytical expressions for the quantization before we go into our next topic of discussion, which will be on the relationships between the pixels in a digital image. So let us see some analytical expressions on the image quantization. And here I mean quantization in intensity. Now basically the process of quantization can be described like this. We have an image which we denote by a variable u over here, and this passes through a quantizer. This block I am calling as a quantizer, which will perform the quantization, and this performs a and 1:1 mapping between this input variable u into some output variable which I am calling as u dot. Okay? Yes, please. Somebody has got a question? Pardon? Okay. I am going to make the letter size bigger. Now, is it clear to you? Okay? So u is the input, u dot is the output of the quantizer. Now tell me, what type of function is this u? No, u is not a discrete. U is a continuous variable. So u is continuous variable. And what about u dot? U dot is going to be a discrete variable, right? So u dot is going to be discrete. That means to say that it can have only some permissible levels, right? Now we can say that the permissible levels of u dot are R1, R2, etc. up to RL. These are the set of values, okay, discrete set of values from which the which this output function can take, okay, out of this discrete set of values, whereas u is going to be continuous. Now if we try to plot a transfer function between this u and u dot, this transfer function of this block, okay, that means to say we will be having the continuous variable u in the x-axis, and we will have the output, that is the discrete variable u dot, okay, in the y-axis. If we try to plot the transfer characteristic, can anybody tell me that what is going to be the nature of that transfer function? Yes, the right answer which somebody has given is that it should be a staircase function, because the output can have only some discrete values, whereas this u is continuous. This u dot is permitted to have only some specific levels, r1, r2, r3, r4, etc., etc., and the function will be something of this nature. This will be the nature of the function. If we allow negative u also, then accordingly we will be having negative u dot. Of course, in this case the negative values do not have much of a physical relevance, because the intensity is always taken as positive, okay, but mathematically we can show any function, okay, any real variable u which can take positive and negative values. Its quantization, its quantized output will be in this range. And let us define this input variable u which I was talking of, okay. Let us define another set which I call as pk, where k is equal to 1, 2, etc., etc., up to l plus 1, okay, where this pk, these are the decision levels, or they are called the transitions. That means to say that when the input variable is between T1 and T2, then the level is going to be R1. When it is between T2 and T3, the level is going to be R2, and so on, okay. So Tk is called as the transition or the decision level of the input variable. Now we will see the expression for optimum mean square quantizer. So we are now going to study an optimum mean square quantizer. What is meant by mean square over here? I told you in the last class that the process of quantization is introducing some amount of noise, okay. That noise is nothing but the difference between the quantized level and the actual level, okay, which means to say u minus u dot, okay. The difference of u and u dot, it may be positive or negative, but the difference between u and u dot is going to give us the error of quantization. And when I say a mean square quantizer, that means to say that we are going to design a quantizer where the mean square error is going to be minimized, okay. So let us see the expression for the mean square error. If we say that this E is the mean square error, then we have to write E as the expectation of what? Expectation of u minus u dot square, u minus u dot, this expression squared, because I told you that the error could be positive or negative, so it is a better thing to take the square of that expression. So expectation of u minus u dot square And if we say that the probability density function, the PDF, of this continuous variable u is written as P of u with respect to the variable u. So if PUU happens to be the probability density function of the continuous variable u, in that case, what will be my expression for this expectation? My expression will be nothing but an integral function of u minus u dot square multiplied by the probability density function, okay, with the variable u, du. So my expression will be u minus u dot square pu u du, okay, and that is going to be within the limits. What? Can anybody tell me the limits of integration? I have already defined my decision levels. The decision levels are Tk, k is equal to 1 to L plus 1. Correct? So, my limits of integration will be T1 to T of L plus 1. Is that clear to everybody? Now, this is the total range which this variable u can have, that is T1 to TL plus 1. Now, we can also write it as the integral for one quantization step, okay, and then we can sum it up for all the quantization levels. Rather, this same expression we can write in a little bit of different manner. We can write this as a summation expression, I is equal to 1 to L integral u minus Ri square Pu u du. Remember, Ri I have already defined. Ri is what? Ri is nothing but the ith discrete level of the quantizer output. Okay. So if I write my expression like this, what will be the limits of integration of here? I mean, what will be the limits of integration here? Can anybody tell me? Not I.
1 to L. I to L plus 1.
You can take up this variable u can take up the values, the decision levels of u are in the, I mean, those are called as Ti, not just simple I. So we have to write it as Ti to Ti plus 1. That's very correct. So it will be Ti to Ti plus 1. Those are going to be the limits of integration. And this thing we have to sum up for I is equal to 1 to I is equal to L. I think that takes care. I mean, it's nothing but the same integral expression which I had written above, okay, from T1 to TL plus 1, which I am now just separating out, writing the individual integrals and summing up over I is equal to 1 to L. Okay. Now, what is going to be the necessary condition for minimization of this expression? Because whenever we are talking of the mean square quantizer, okay, as I told you in the beginning that we are going to minimize this error. So what should we do? We should differentiate with respect to Tk, also with respect to Rk. Okay, let us see that what do we get when we differentiate with respect to both Tk and Rk. If we differentiate with respect to Tk, the expression which we get is like this: Tk minus Rk minus 1 whole square Pu Tk minus Tk minus Rk square pu tk, and this is going to be equal to 0. Again, for the differential with respect to rk, we will write like this: del E del rk is going to be 2 times within the limits tk to tk plus 1 as before, u minus rk pu u du, that equates to 0. Now if we simplify these two expressions, okay, after simplification, tk is going to be equal to rk plus rk minus 1 divided by 2, and rk is going to be integral tk to tk plus 1 u pu u du divided by integral within limits tk to tk plus 1 pu u du. Okay, this is what we get as the expression for tk and rk. tk is expressed in terms of rk. Okay, so this is what we get, and rk is being expressed in terms of u and pu. So rk, that is to say the quantization levels, okay, are obviously dependent upon the probability density function if we are trying to achieve a mean square quantizer. Is that clear to you? You can verify these expressions yourself and do this simplification. You will get this one. Now, so that means to say that the probability density function of this u, variable u, is very much important in these expressions. Now, what kind of a probability density function do you think is reasonable to assume? A Gaussian, yes, somebody said Gaussian, and Gaussian probability density function is reasonable, no doubt. In many of the cases, the probability density function which we get from the image histogram, that shows us a Gaussian function. Okay, before we go into the Gaussian, okay, I think I can leave that as an exercise to you, that how to compute the quantization expressions for a Gaussian probability density function. To begin with a very simple case, we can start with a uniform probability density function, and let us see what we reach. So uniform probability density function means I am assuming that within Ti and within Tk and Tk plus 1, okay, the variable u has got a uniform probability density function to be anywhere in that level. Absolutely flat, uniform PDF. We assume that. So if we do that, then mathematically this pu, the PDF function, we can write as pu equals 1 upon TL plus 1 minus T1, where what are going to be the limits of u in this case? T1 to TL plus 1. Okay, so this is when we have u lying between TL plus 1 and T1, and this is going to be 0, okay, otherwise. So this is our probability density function. Agreed? Now, if we substitute this expression for in our earlier equations, then we obtain Rk equals Tk plus 1 plus Tk divided by 2, okay, which gives us obviously Tk minus 1, okay, that will be equal to tk plus 1 minus tk. This is going to be a constant, and that constant by definition we are calling it as the quantization step q. So q is nothing but the quantization step, which is nothing but the difference between the two decision levels, tk minus 1, and this transition difference is going to be equal to tk plus 1 minus tk, and this by our definition is going to be q. Okay, and in that case we have to write, we can write q as TL plus 1 minus T1 divided by L, because there are L number of decision levels between T1 and TL plus 1. So obviously the total difference TL plus 1 and T1, the total difference divided by L gives me the quantization step q. Okay, and using this I can write tk equals tk minus 1 plus 1 quantization step q. Okay, and if I try to substitute this definition, okay, this definition if I try to substitute over here, okay, I am going to get, you can verify this, Rk is going to be equal to tk plus q by 2. So the kth quantization level is going to be equal to the kth decision or the transition in the kth transition in the continuous variable u plus exactly half the quantization step tk plus q by 2. You can verify this from this expression. Now we have assumed that the quantization error is uniform in the range of minus q by 2 to plus q by 2. So we have assumed that quantization error is uniformly distributed over minus q by 2 to plus q by 2. Okay, and hence we can say that this E, okay, is going to be equal to 1 upon q within the limits minus q by 2 to plus q by 2 u square du, and this gives us q square by 12. This is the expression of the quantization error, okay, in terms of q. I think this expression we already know is, for time domain signals when we do the quantization we get the same expression. Now if A is the range of the variable, u, okay, then what is going to be the quantization step? Let us assume that we have B as the number of bits in the quantizer. So the quantizer is designed with B number of bits. If we have that, then what is going to be the Q in terms of A and B? Can anybody give me the answer? A is the, I repeat, A is the range of the variable, okay, and B is the number of bits I am using in the quantizer. So obviously we have 2 to the power B levels, okay, and if I divide that by A, that simply gives me the quantization state Q. So I think already the right answer has come from the audience. So this Q is going to be A by 2 to the power B, okay, and if A is the range of the variable, then we can write the variance as sigma square u, okay, that is going to be a square by 12. This also you know, okay. A being the range of the variable, we have the variance as I have assumed it to be uniformly distributed. The variance is sigma square u will be equal to a square by 12. So our mean square error E divided by the variance of the signal sigma square u, what is going to be the expression? I put back my earlier paper over here. This was Q was equal to A by 2 to the power B, okay, B being the number of bits. And now what I am interested in computing is the ratio of this mean square error E with respect to sigma square u, and sigma square u I know it is a square by 12. So obviously this is going to be q square by a square, because I know that E is equal to q square by 12, sigma square u is equal to a square by 12, so I simply get q square by a square. So I get it as q square by a square, and substituting the expression for q, which was q equal to a by 2 to the power b, okay, then we have this as 2 to the power minus 2b. Now this is a ratio. What kind of a ratio is it? E is what? Is it a signal or a noise? E is a noise, because E is the quantization error, so that is our noise. And where is the signal component of it? In sigma square u we have the signal component. So now what I should have is, if I want to compute the signal to noise ratio, okay, I should write it as what? Correct. I should write it, SNR is to be represented in dB. So I should write it as 10 log to the base 10, okay, sigma square u divided by E. Is that correct? And that is going to give us 10 log 2 to the power 2b, and the right answer has already come. Some person has rightly said that it is going to be 6d so much of dBs. So you just see, if I increase d, if I increase b, that is the number of bits, if I try to increase, then obviously that also improves my signal to noise ratio. But remember again my discussion in the last class, if you keep on increasing b, you are facing problem in the storage space, right? So this expression we can keep in mind. And just note one more interesting aspect of this type of a quantizer. Just see that we have got Rk as Tk plus 1 plus Tk by 2, and this is going to be valid for all k's. And this means to say what? That the quantizer which we have got satisfying the mean square error criteria, the quantization that we are getting is a uniform quantizer, okay, and since it is following a linear relationship, this is also called as a linear quantizer, or there is yet another name, okay, for this kind of a quantizer which I have designed, and please remember that this is called as the Lloyd Max quantizer. This is the Lloyd Max quantizer, okay, which is just now shown. So here I have got this expression assuming a uniform probability density function. But obviously, if my probability density function of u is going to be something like this, as somebody was suggesting that we should have a Gaussian probability density function. So this is my axis containing u, and this axis I am having pu by pu of u, okay. This is my probability density function. If I have it like this, okay, take the Gaussian expression and I think you can take it as a good exercise to find out that what type of quantizer do you get. Okay. Now one thing that so far, whether it is in the spatial digitization, okay, or in the intensity quantization which we have rigorously discussed today, somehow we are always considering the cases where the sampling and digitization, everything is absolutely uniform. Uniform in the sense, if I have the, if these are the defined grids of the image space, okay, if that entire image space is divided into a two-dimensional grid like this, and if we sample at every intersection of the grid, then we are going to pick up samples here. Okay, this is in the x direction. In the y direction, we are going to pick up the samples like this. So totally this x and y area gets filled up, and we get sampling in both x and y. And if the grid spacing column wise and the grid spacing row wise is going to be uniform, that is going to give us a uniform sampling. Okay, and somehow we have tried to assume this aspect that we are considering a uniform sampling. Now, do you think that it is mandatory for us to always consider a uniform sampling? Let us say, for the sake of argument, that somehow I tend to remove this restriction. You need not quantize uniformly, okay? You are free to choose your sample space, your sampling intervals. Meaning, if I wish, I may have this kind of a sampling spacing in x direction, and in the y direction that is to say, in this direction I am drawing these lines, so these are my samplings in the y, and these lines give me the samplings in x. This is the x, this is the y. So this is how my sampling grid will look like. So it is going to be absolutely non-uniform. Okay, just see, possibly somewhere in this region, okay, this entire region, I am picking up such a big region, okay, and just encircling this. Just see, I have picked up only 1, 2, 3, 4, 5, 6, 7, 8, 9 samples. And over such a small region, okay, I have picked up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 samples. So totally non-uniform, isn't it? But do you feel that we should do that? Yes or no?
Yes.
Okay, the answer that people have given is yes, but I'd like to get into a bit of discussion on this, that why our answer should be yes, why should we do that? And if so, when should we do that? Always or sometimes? What is the answer?
The probability of occurrence is value in those spaces where we are selecting more samples.
Probability of occurrence of the values in which we are seeing more samples.
There we should take a very closer levels.
There we should take a closer levels. I think that is the answer which somebody has given me. Any other answer? Anybody wants to suggest something more? Okay. Now, more or less what he has said is correct. Thing is that if we find, Okay, let us now talk qualitatively. Let's not go into the probability density function and all those mathematical expressions. Let us go into the, let us talk from a qualitative point of view. If we find that the image has got more amount of details in this region, this encircled green region which I have, okay, if the image has got more details, then it is reasonable to pick up more samples in this area. Whereas, in this region, okay, if the details are missing, if it is a uniform intensity region more or less, we can pick up less number of samples. This kind of an argument we can give, obviously. Like say for example, in a TV frame, okay, when just one person is being shown against a background, okay, you can pick up the details of the face for that particular person. But you did not have to pick up every details of the background. It is something like that, okay. But of course you can't do it with all the images. Supposing there is a big public gathering somewhere, okay, there is a large mass of people and you have taken a photograph of that. So your photograph is filled up with all the with all the people your photograph is being filled up, and there is no particular region which you can pinpoint and tell that here I have more details, here I have less details, okay. So for such kind of things you can't think of a non-uniform sampling. So non-uniform sampling we should only do wherever such kind of things are there. Of course, from a practical consideration, doing a non-uniform sampling is possibly a little bit problematic, because what we have to do is we have to analyze the image first and we have to get the details a priori. So we have to do some kind of a processing in the image to know that where the details are clustered and where the details are less. Somebody was saying finding out the probability density function. If we, even if we try to do that, okay, we have to do a lot of prior computations beforehand, and that is, I think, not really feasible. So that is why uniform, non-uniform quantization you can do only when we know that over a particular region the details are going to be more and over some regions the details are going to be less. If that is known a priori, then we can afford to do a non-uniform sampling in the spatial, non-uniform sampling spatially in the x and y direction. So this was our non-uniform sampling. Now, likewise, we have also assumed that in the intensity domain, okay, we are digitizing in uniform steps. Now, should we also think of digitizing with non-uniform steps? Okay, just now we have seen one thing, that if we have a uniform probability density function, okay, then we are automatically getting a uniform quantization levels. But if the probability density function is not a uniform PDF, do you think that it is reasonable to expect that we can get possibly a better result, okay, by going in for a non-uniform quantization? Meaning, supposing my intensity distribution is something like this. Again, I am considering the probability density function of u. This axis is u, and this axis, it is the probability density function of u. And supposing we have got a PDF something like this. Supposing this is my total range, I was talking of T1 to TL plus 1. Supposing this is my TL plus 1, the maximum, T1, that is the minimum, and this is the kind of a probability density function that I have got. Okay. Now, if we quantize like this, if we say that we will have uniform levels. So, quantization after all leads to a, uniform quantization will mean that this T1 to TL plus 1, this particular interval will be divided into some discrete steps. Okay, and so far we were assuming uniform discrete steps, so it was something like this. If we take uniform discrete steps, we get something like this. This would be possibly our R1, R2, R3, etc., up to RL will be something like this. But just look at this probability density function once more. This is our probability density function. Now when we have this kind of a PDF, just see that over this region and over this region we have got the probability density function value is quite small. That means to say that we have lesser number of pixels, okay, in that particular intensity. Means in this particular region and in this particular region we have got lesser number of pixels, whereas most of the pixels are having intensity values in this particular region, correct? So that means to say what? If we decide to choose a non-uniform quantization levels, what should we try to do? Any suggestion? The green region or the orange region? Which one should we take? This encircled green or the encircled orange? The encircled green region we should take, because there we have more number of pixels. So if we decide to increase the quantization spacings in the less populated area, and if we reduce the quantization spacings, make it more close, make it more packed in this particular region, this green region where there are more number of pixels, okay, in that case we can have a possibly a better quantization, because we are taking care of the intensity details in this region and we are relatively ignoring the lesser populated areas. Is that understood? Okay. So definitely the aspects of uniform and non-uniform quantizations are involved over here, but like the case of non-uniform sampling in the spatial domain, we must also remember that non-uniform digitization in the intensity domain is also not feasible always. Firstly, that if you want to do a non-uniform quantization like this, again you have to find out a total distribution of the pixels. You have to find out you have to find out this probability density function. Of course, it's not very difficult to find out the probability density function of intensities. What you can simply do is that you can, in the y-axis, you can plot the population of the individual pixels. Like pixel having intensity unit 1, you get their population. Pixels having intensity unit number 2, you get their population, so on up to pixel having intensity level of 256, you get their population. So like this you show a population distribution, and in the limit that these intensity levels are close enough, okay, that population distribution, or what is called as image histogram. Of course, we will come to the discussion of histograms little later. So that curve which we call as histograms, from that we get an idea of the probability density function. And once we get the idea of the probability density function, possibly we can attempt to do a re-quantization by picking up the, by redistributing the quantization levels, so that we get more closely packed quantization levels in the regions having details and less closely packed in other regions. Any questions or queries on this? Yes, please.
Sir, you are talking about this non-uniform sampling, sir.
Yes, please.
Sir, for this one we should know about the PDF initially.
Yes, the question which you raised is that for non-uniform sampling we should know the PDF beforehand. Yes, continue your question, please.
So now We don't have any digitized image a priori, sir. We don't have any a priori.
We don't have any digitized image a priori, then
How is it possible?
how is it possible? Okay, so he has raised a very good question that we don't have any a priori idea, so how we go about the quantization in the first place? So that is why I use the term of a re-quantization. So what you do, at first you quantize with uniform intensity levels, okay? Then after seeing the histogram, okay, you redistribute the levels once more. So that is why I said that you can only do a re-quantization. There will be very few cases where you will know a priori that this is going to be my expected intensity distribution. When you don't have such kind of an assumption, okay, that this is going to be our expected intensity distribution, the best thing to assume is that the image is having uniformly distributed intensity function. So going for a uniform quantization level, once you find that really speaking it is not uniform, go over for a re-quantization. Any other questions? Alright, so I think in the next class we will be talking about the relationships between the pixels, okay, because we have already covered the aspects of sampling and quantization. So with this it will be easy for us to proceed further to have some basic definitions of relationships between the pixels. Okay, thank you.